Okay, we're back for part 2. It's Mrs. Allen, and we're doing chapter 0 prerequisites, AP Calculus AB, parametric equations. So looking at continuing, we have the example 1 that we finished, and we drew the parametric graph, and it has to do a lot with direction, where you start and where you end, and the t, the parameter, governs the function. So now we're going to look at circles. So with circles, there are applications where t denotes time, an angle, or the distance a particle has traveled along its path from a starting point. So there are different things t can stand for. Sometimes we use t as an angle, other times we use theta. Parametric graphing can be used to simulate the motion of a particle, such as the Ferris wheel, where you have vertical motion and horizontal motion of the Ferris wheel as it's moving. So you can picture that each point has a horizontal distance from the center of the Ferris wheel, and it has a vertical distance from the bottom of the Ferris wheel. So there you go. And so that's a really good example to use. For parametric equations, describing the graph of a relation determined by trig functions. So this we have to deal with a little bit differently, and I think I did an example of one in class, and here is another one. So if I say that x is equal to 3 cosine t and y is equal to 3 sine t, then as you're graphing your function, your t value goes from 0 to 2 pi. We want to find the initial points, if any, and indicate the direction in which the curve is traced. So with this one, you'll, as you go, and I kind of like gave the secret away, but it is a circle. But so if we find the initial point when t is equal to 0, we get x is equal to 3 times cosine of 0, which is 1. So that's just going to be 3, right? Okay, and then if I have the sine, 3 times sine of 0, that's going to be 3 times 0, which is 0. I guess I have enough space. I can type it in here. So that means the first point is going to be at 3, 0 that I have right here. Okay, so that's where, and on the graph, I'm going to write t is equal to 0. At t is equal to 0, this is the start point, and that will be at 3, 0. And that's an x and y coordinate, right? Okay, so at pi over 2, we're going to get 3 times cosine of pi over 2, cosine of t, is 0. So this is 0. And then 3 times sine of pi over 2 is 1. So that's 3. So now we have the point 0, 3. Now my graph is not quite squared up, so it looks more like the grid looks like a rectangle instead of a square. So it might look a little bit more like a squash circle. So here we have 3 times cosine of pi is negative 1. So this is going to be negative 3. And 3 times sine of pi is 0. So this is going to be 0. So we have the point negative 3, 0. It's right here. So now I want you to notice as t progresses in order of a rotation, as you rotate counterclockwise, positive angles, then we start at t equals 0, we go to t is equal to pi over 2, t is equal to pi, t is equal to 3 pi over 2, and then we get back to t is equal to 2 pi. We're back at 3, 0. So when I plug 3 pi over 2 in, I get cosine of 3 pi over 2 is 0, so we end up with 0, and then 3 times sine of 3 pi over 2 is negative 1. So we end up with negative 3. So 0, negative 3 for this point. And you can kind of see that the circle goes like this. Oh, it's kind of sloppy here. Let me make it a little bit neater. So principle of charity applied to... So, and here's the arrows for the direction. And you guys know the point, so I'm not going to write the ordered pairs on those, okay? Now, remember that x squared plus y squared is equal to r squared for a circle, right? So if I look at these, I can figure out what's going on here by saying, well, x is 3 cosine. So if I take both of these, this is the equation for a circle, right? You know this from the past, where if it's any circle, x is equal to r cosine theta, cosine t in this case, and y is equal to r sine t. So now this is a circle. It's a So if I square this, it's a circle with radius 3. If I square this, I get 9 cosine squared t plus 9 sine squared t is equal to 9. The radius is obviously, I'm going to move this over here. And then if I factor out a 9, right, 9, you'll see that it is certainly true. We get cosine squared, divide everything by 9. Cosine squared plus sine squared t is equal to 1. Okay. So with the parametric equations, you can kind of see, oh, that's kind of a verifying that, yes, in fact, that it is the circle with radius 3. So just a kind of a roundabout. We talked about cosine squared plus sine squared is equal to 1 today. So there you go, getting ready for that. Now we have the ellipse. The ellipse is a little different than the circle. We have x and y there, and we could easily divide. And I could have divided by 3. I could have said x over 3 is equal to cosine squared. Or cosine. I could have said that y over 3 is equal to sine, but that's not what I'm doing. In this next problem, that's what I am going to do, where we have cosine t and then y over 3 is sine t. So coming down to this next problem, we have an elliptical problem. And so with an ellipse, a little bit different. I'm going to throw one in there here. So parametrizations, when you have a hard time saying it, you know I do too. Parametrizations of ellipse are similar to parametrizations of circles. Recall that the standard form of ellipse centered at the origin is this. Now, when I say recall, many of you are coming from different places. Most of you are coming from different places and different amounts of proficiency when it comes to working with what we call conic sections. So if you recognize that, great. If don't, hang on. It's no worries. You'll see it. And you do have a graphing calculator, and you'll pick things up quickly. So for x is equal to a cosine t and y is equal to a sine t, we have that is the same thing as true that we just did with the circle. So let's see how it works. If I ask you to graph a parametric curve where x is equal to 3 cosine t and y is equal to 4 sine t without a graphing utility, to see how it's going to match up with its rectangular or Cartesian coordinate equation, I can take both equations and I can say, all right, well, if we have this with a unit circle, right, I know cosine squared plus sine squared, no matter what the argument, is going to be 1, right? So just a little note aside from previous lessons that, let me stick that here. So that was kind of like a remember this. So now if I say I have x is equal to 3 cosine t, I'm dividing the x equation by 3, and I'm dividing the y equation by 4. So I'm going to start off, I'm going to say I know that cosine squared t plus sine t, no matter what the angle is, if those are the same angle, t's in this case, then the result is going to be 1, right? So now if I look at cosine being equal to x over 3, if I put an x over 3 here and I square it and then I say plus, well, the sine t is y over 4, and then I square that, and that's equal to 1. Then I get this equation, x squared over 9 plus y squared over 4 squared, which is 16. So that's equal to 1. Now we can rewrite this in different ways. This is a convenient way to write this. And so what you're going to have in the end, those of you that are mathematically astute and you are like, I want to know what this graph looks like, are probably pulling out your graphing calculator right now and going, I gotta see. So in this case, you're going to have, here's the origin's in the middle, And this is, the y is what we call the major axis. So I'm going to put points at 0, and all I'm going to do is just show you so you can make sense of it. Because the bigger number is with the y, 0, 4, and 0, -4. This is like an a squared. I would show you the point, but I just want you to kind of make sense of it a little bit. And then on the minor axis, the x is the minor axis. So since, and I'll write the form of the equation down here, it's x squared over, it should actually be y squared over a squared plus x squared over b squared is equal to 1 because the b is less. So you can see that a squared is equal to 16, a is equal to 4. Here, b squared is equal to 9, and b is equal to 3. So with that, I'm going to put the, I have plus or minus. So this is what your equation looks like. Oh, I don't want red, I want blue. Here, you're going to come down this. So kind of like a squash circle, right? Now there are things called foci and other things, but when you put it in a graphing calculator, you have to actually solve for y. Parametric equations, you don't have to. If I solve an equation that looks like this, if I solve this for y, I'm going to have to use a plus or minus, so I have to actually put in 2 equations. We still have to put in 2 equations for parametric, but it's not as easy as I'd like to. If you're using Desmos, Desmos can graph this easily. You might want to check, put it in like that for one equation, and then put it in parametrically for the other equation. So that's all I have for your lesson. I just had a few examples for you to go through. Bring your questions if you do the homework and you're trying to figure them out, whether it's a circle. If you think about it with the worksheet that we did, we graphed a line. We graphed a parabolic kind of shape. We graphed a circle, and then we graphed an ellipse. So you had some kind of funky graphs that were kind of wonky looking sometimes, but really cool. And I think you'll like that about parametrics. Again, they're handy because what you're doing is you are able to look at the horizontal behavior and the vertical behavior as 2 separate functions. And so that's it for today. It's going to be Alanator out, and we'll see you when we see you. Have a good day. Bye.